the surface S could still be described as that one that we graphed, the hyperbolic paraboloid. We could still describe it as xy, f of xy, as x and y vary over the unit circle, the unit disk. But now we're not trying to find the surface area of this surface. We're trying to integrate a vector field over it. We've got a capital F. Let's make the capital F fairly simple. 0, 0, z. It's going to be a three-dimensional vector field. And it's nicest when they're simple. F of xy is still x squared minus y squared. I forgot to write that. If I make this the positive x-axis, this the positive y-axis, this positive z-axis, it's some sort of saddle surface looking about like this. Like a Pringles chip, kind of. Actually, it goes down a little bit more over here. I should draw a little bit more like that. Something like that. Imagine that as like a saddle going into the screen. Okay. If you're sitting on that, you'd either be facing you, or your butt would be facing us. Okay. One or the other, you'd be sitting in the saddle. We're not, again, trying to find the surface area of this. We're trying to do, in this section 14.6, we're trying to do one of two things. Either assume we've got a density function describing the area density of this thin plate of metal shaped like this, and integrating it to trying to find the mass. That would be a scalar surface integral. Or we're trying to integrate the vector field, which is what I'm focused on right now. And this particular vector field has vectors that, well, when z is positive, they point straight upwards, and they get longer as z gets larger. When z is negative, their arrow is pointing straight downward. And what the integral of the vector field over the surface is supposed to represent is the flux across the surface. And maybe I better change the vector field. I think by symmetry, the answer would be 0 if I use this one. Let's use z squared instead. So these are not going to point downward. They're not going to point upward still. Effectively, when you compute the surface integral of the vector field, you're computing something called the flux of the vector field over the surface. If these vectors represented velocity vectors of some fluid, say water, in a tank, say, and if this potato chip or saddle kind of shape was a screen which the water could flow through, the integral of the vector field over the surface would represent the flux. Effectively, amount of water going through the screen per unit time. Now, again, I'm not an engineer. I'm not a physicist. I just kind of make some sense of that at the level of the book. If you're studying fluid mechanics, you could try to make more sense of that, describe it more precisely. This even has applications, though, beyond fluid mechanics. It has applications to electrostatics, electromagnetism. The vector fields are no longer velocity vector fields of fluids. They are like force vectors for, electric fields or whatever. But you can still give the integrals meaning. Effectively, what you're trying to do in integrating the vector field over the surface is you're integrating the vector field dotted with what's called a normal vector to the surface. N is a normal vector. What normal vector? There are lots of normal vectors. Any surface is going to have lots of normal vectors. If it's not a plane, they're going to point in different directions. It's not a constant normal vector. It is changing over the surface. It's also a unit normal vector. It's got unit length. It's changing over the surface because the surface normal direction is changing. Normal means perpendicular to the surface, and it's changing as you go over the surface. Technically speaking, the surface has to be something called an orientable surface. Most ordinary surfaces that you're used to, like graphs of functions or spheres or ellipsoids or even something called a torus, which is like a donut shape, are orientable, you can consistently define a continuous outward pointing normal vector. But there are some non-orientable surfaces. A Mobius strip is the most common example, where you cannot consistently define an outward pointing normal over the entire surface. Which direction should n go in this picture? It's up to you. You can choose which direction you want n to go. It makes more sense since the velocity vector field F is pointing, generally speaking, upward, to let n be an upward pointing normal vector, not downward pointing. Then we should expect this flux integral, that's what this is called, a flux integral. We should expect it to be positive because the velocity vectors are pointing upward. But how do you compute it? Realize that you could define n, first of all, using your parameterization by doing this. Taking the cross product of RU with RV and dividing by its magnitude. Why? Why does that work? Sorry that I always have to do so many error pictures here. Okay, got the surface. RU and RV are tangent to the surface. They parameterize the surface. Dare I try to make a picture? There's your surface. You're at a given point. R of UV parameterizes the entire surface as U and V vary, effectively creating unions of parametric curves, maybe as U varies that look like this, and unions of other parametric curves, say as V varies that look like this. At the given point, RU is effectively a tangent vector in this direction. That's RU. Think of V as constant. It's a parametric curve. The tangent vector is a velocity vector really in that direction. RV would be in the other direction. I drew them so they could kind of look like they could be perpendicular, but they wouldn't have to be perpendicular. As long as they're not parallel, you can form the cross product, and it's going to be perpendicular to the surface. RU cross RV. Normal to it. To create a uninormal vector, just divide by its magnitude, as long as you're not dividing by 0. And you won't be dividing by 0 as long as RU and RV are not parallel. When they are parallel, that's kind of a degenerate case, and we want to mostly try to ignore that case. So anyway, once you've defined that to be your unit normal vector, based on your parameterization, then you can say this integral becomes, fancy S is the surface itself. Well, okay. Let's change that, sorry. Let me not specify what the region of integration is yet at the moment. Replace n with RU cross RV divided by its magnitude. But then we're replace dA, or ds, excuse me. Replace this ds, this small element of surface area, with the same element of surface area that we used to figure out surface area from 14.5. Replace ds with the magnitude of RU cross RV dA, where now the region of integration would really be a rectangle, which we'll specify by R in a UV plane. And magically, these magnitudes that involve square roots cancel, they go away. And so no, you don't have to work with square roots anymore. And you ultimately do an ordinary kind of double integral over a rectangle of the vector field dotted with the cross product RU cross RV. So you still do have to figure out the cross product. But I guess the good thing you don't have to do is you don't have to find its magnitude. So the integral doesn't typically involve a square root. So with this particular example, let's go back to doing it the way the book does. We will use this parameterization for RUV and these derivatives and this cross product. We still have to use that. This cross product is a three-dimensional vector. Take the cross product of two three-dimensional vectors, you'll get a three-dimensional vector. We want to dot that with the vector field. This is a new example here. Let's define the vector field. I usually, as a default, like the input to be a list again. There are good reasons for that I haven't gotten to yet. But it's a simple vector field, 0, 0, z. Z squared, excuse me. Always pointing straight upwards with different magnitudes representing different velocity vectors for a fluid. The velocity vectors get longer the further away you move from the XY plane in either direction, meaning the fluid particles, the water molecules, are moving faster the further you are away from the XY plane. What happens if I dot that with a period with that vector? That is RU cross RV there. And simplify. It's nice and simple. Amazing. I'm sure what happens to make it nice and simple is using trig identities, probably, cos squared u plus sine squared u equals 1 is used. If we didn't simplify, would we see that? Well, okay. Sort of. It's with a minus sign, you have a cos squared u and a sine squared u. Stuff must cancel, is what must happen then. So that's the thing to integrate. Now with respect to u and v. Oh, well, not quite. I forgot something. I forgot to replace x, y, and z with how they depend on u and v. Yeah. That's R. And because I've defined f with a list like this, I can actually just plug in the R like this. Is that right? What happened there? If we did the original one, what's the relationship between these two things? You would replace z. You see on negative v times z squared. You do see something squared here, but then you see a fifth power there. You're replacing z effectively with this thing. That's got to get squared. So I can see I get a v to the fourth. Oh, I do see a cos 2u. There's a double angle formula that Mathematica is using to get this. Cos 2u, you look up a double angle formula. Double angle formula. Cosine. Effectively, it's using cos 2 theta is cos. It's probably solving this equation for cos squared theta. It's probably using the fact that cos squared theta is 1/2 plus 1/2 cos 2 theta to help do the simplification in the end. But this would be what to integrate then. U going from 0 to 2 pi. V going from 0 to 1 in the parameterization. Looks like we're going to get a negative answer. That doesn't make sense. Negative pi over 6. What am I getting wrong here? Oh, what I might be getting wrong, and this could be a common thing. What I might be getting wrong is with this parameterization, the n vectors could be pointing downward. And I wouldn't know that without graphing them. How could I figure that out? There's your cross product. I could plug in, say, u equals 0, v equals 0 into that and see if I get a vector pointing upward or downward. It's probably pointing downward. I got my dot here. Slash dot. Or 0, 0, 0. Okay, pick something slightly different. Still on the surface. How do we get a point on the surface? Well, it'll be on the surface no matter what U and V are. Let's pick a point slightly different from 0, 0. Yeah, the Z component is negative. It's going to be pointing downward. So that was my problem. If I want to find the flux through the surface in the upward direction, the vectors in F are pointing upward, which I'm hoping is going to be a positive answer. I need to make sure I got the right direction for N. And it's not obvious without plugging a point in like this, which general direction N is pointing upward. But because we plugged in this point slightly different from 0, 0, and we got a negative Z component, it's not pointing straight downward because the X and the Y components are not 0, but it's mostly downward. We could also probably plot these vectors with graphics 3D and vector. I won't go into details, but you probably could get Mathematica to actually graph the vectors too to see that they're pointing straight downward. So what this means is you actually need to do the dot product with the opposite of this. Put a negative sign in here, like that. Then we don't get a negative sign there. Get rid of that negative sign. The answer is pi over 6. About 5.52359. I think effectively what this represents is the amount of fluid crossing the screen per second. But what would the units of the vector field have to be for that to be the case? And what would the units for the answer be? I think, you could think of the vector field, if it's a velocity vector field, as being in meters per second, say. Or maybe if it's water, maybe you prefer centimeters per second. And essentially the NDS is in square centimeters. The ds is a small element of surface area. The ds itself is in square centimeters. Actually, maybe I should just think of that as being the ds. F dot n is in centimeters per second. The ds is in square centimeters, giving you a product, so to speak, that's in cubic centimeters per second if F is a velocity vector field in centimeters per second. Using the integral doesn't affect the units. So yeah, if F is a velocity vector field, where the arrows represent velocities of, say, water molecules in centimeters per second, the magnitude at least is centimeters per second. And when you dot with a unit normal vector, it doesn't change the units. It's still in centimeters per second. The ds is a small amount of area along the surface in square centimeters. Effectively, the product is an amount of fluid volume-wise in cubic centimeters per second that's passing through that small little bit of surface area per second. But then when you integrate, you're adding those all up and getting the total amount of fluid that passes through this permeable screen every second. 0.52 cubic centimeters every second. Have to use your imagination, right? And it's very difficult to visualize. You can use the technology to visualize it somewhat, but knowing exactly what the answer is going to be is very difficult. And we could have used a more complicated vector field here, where maybe some of the arrows are pointing upward, and some are pointing downward. Effectively, some of the water is going upward through the screen over here and going downward through the screen over there. And it would not be clear in such a situation whether the flux, say, in the upward direction is positive, negative, or 0. That kind of thing could happen too. There is another kind of integral. Let's do the same surface again. So it's the same surface as before. Still this saddle shape surface described with R of UV. But instead of integrating a vector field, you integrate a density function. Delta of XYZ, say in units of mass per unit surface area, like grams per square centimeter would be the units of that kind of thing. We are talking about like a thin sheet of metal. Integrating delta over the surface is supposed to give you the mass in this case. This would be in grams per square centimeter. This would be in square centimeters. ds is a small element of surface area, giving you a product in grams. This is going to give you the mass. But how do you actually do the integral? You have to replace ds with, well, let's just write this as delta. Sorry. What's the least confusing way to write this? You have to integrate the function delta, leave some space for the inside of the parentheses. Replace the ds with the magnitude of Ru cross Rv dA over some rectangle in the UV plane. And x, y, and z need to get replaced with how they depend on u and v. What goes in there is x of uv, y of uv, and z of uv. So that is more like the assignment you just turned in, except this doesn't give you the surface area of the thin sheet, but the mass when you've got a density function. So it ends up being harder integrals typically. Same situation, we'll use the same exact surface defined by f and the corresponding parameterization with the same derivative, same cross product, same square root. But now we also add in here a density function, delta of x, y, z. That's a scalar value function. It's not a vector field. You know, whatever formula you want, 2x squared plus 3y squared plus z squared or something like that. Maybe I should use curly braces. What do I want to integrate to find the mass if that's the density function? I want to integrate delta of R of UV times that magnitude again. That's going to involve a square root. Times, where's the square root? It was back up here a ways. Yeah, it's simplified to this. It won't always simplify quite so simply. That's the function to integrate. And I can't imagine that that's doable by hand. So use and integrate. Copy and paste the whole thing if you like, or you can also copy and paste this thing too. Once again, u is the angular coordinate going from 0 to 2 pi. V is the radial coordinate going from 0 to 1. If this is the density function for our potato chip shape in grams per square centimeter, whatever we get for this integral should be the mass, about 8.49 grams. Can we make sense out of that? Could we have even predicted approximately what the answer would be? I think so, but it's tricky. You'd really want to plot this function somehow over the potato chip shape somehow. And the only way I know how to do that is contour plot 3D. Oh, we are talking about the potato chip shape. And the output of contour plot 3D is confusing though. You get a bunch of surfaces. And what these surfaces represent are level surfaces of the function. Places where this function is constant in output. And because it's adding together a bunch of squares of the variables with positive coefficients, these things are ellipsoids, three-dimensional versions of ellipses. The other downside is you can't even move the cursor over this to see approximately what the output of the function is along these things. So while in theory I could try to use these to estimate like the average density of the potato chip over its entire surface area, and then multiply by the surface area to estimate the mass to see if this answer seems reasonable, that seems like a difficult thing to do.